Okay, today I will just go start by the chapter 10. So I will just review some parts. Hopefully not really that complex. So 10.1 is curves defined by parametric. Okay, now we have terms parametric, okay, in which I will uh, give some illustration. So parametric means having uh, parameter. Okay. Okay. Usually, our functions is defined by let's just say y is equal f of x. Okay. It can be anything. Let's just say this is normal like exponential or maybe parabola. Okay. Let's say this is y f of x. Okay. And of course, this normal functions is y f of x is if we look the graph, it's the regular one-to-one functions, right? One-to-one. Okay. But however, okay, if we define or if we look at another curve, maybe like this, so it's still y and x. Okay, it might happen. Okay, it might happen. The best way to illustrate or to visualize what this red line means is, I believe in physics you learn about the kinematics, right? Kinematics, the velocity, distance, time, right? And if you use for example, the distance functions, distance, right? Yeah. Usually it will have, let's say x or s, usually s, right? It's usually having t, okay? Maybe t squared plus 2t, maybe. And intuitively, and maybe you can prove that also in physics, you can derive the distance to velocity, in which you get the idea of derivative in physics, in kinematics, and you can get the accelerations in which too. Okay. But this is just an illustration. So probably if we look at this red line as movement, okay? Movement, an object moves. So x and y define a position. Okay? X is the horizontal distance, and the y is the distance in vertical. Okay? So if you say that in every t, the object moves, okay, and change in position. So maybe I can write like, this is just an example, okay, and I just draw randomly. So maybe the object moves based on this arrow. Okay. So maybe here is t equal 0, t equal 1, blah, 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 and t equal maybe 2. Okay. So from 0 to 2, we can look at the movement of the object that it's moving. Okay. It's moving. But then, if we are taking the parametric equations as it is, okay, t is time, then we are if we are narrowing the definitions. Actually, what the parametric means, it's not only time, okay, So not only t as time, but it can be anything. It can be angle like theta. It can be any parametric variables that you can parameterize into equations. Any equations that can be parameterized. Like for example, if we are looking t as time, it would be weird if we are taking t in negative, right? Can time be negative? Maybe our mind, oh, how time can be negative? It means we are traveling back, right? But actually, t it can be anything. Okay? It can be negative also. So we can start with t -1, -2. Okay? So parametric equation is any variables that can be parameterized into x and y. Okay? And usually we are writing the parametric as the equation as xt or yt, or maybe it's easier if I write x like this. The same as in your textbook to make it consistent. We can write maybe like this one. Okay. So like for example, if I have x is let's say t squared minus 2t, and y is t plus 1. If we are looking at any t that we can think of, okay, if we start from negative something, 0, and then 1, and 2, and 3, we can make a graph. Okay? We can make a graph. And actually, if you are drawing the graph from these two equations, we can have at least, can I make parabola here? Oh, wait. Okay, that's good. Okay, probably like that. So if you check any t, like 0, 1, 2, for any x and y, you will get the parabola. In any way, if you see parabola, usually it has a relation between x and y. Usually we have this kind of parabola, it's x squared, right? But this one is y squared. One way to see this parametric one is to eliminate the t, and we can substitute and make a new equations. Okay. For example, if I write t as y minus 1 and substitute to this x, okay, I can have y squared minus 2y minus okay, y squared minus 4y and plus 1 plus 3, right? Yeah. So we can also simplify the parametric equation and write down the parabola. But sometimes we have parametric equation, and maybe it's difficult to translate or transform to the normal parabola. Or when you transform, it becomes more complex, and it seems when you solve the problem, it doesn't. You need another way to solve it sometimes. But if you are seeing this x and y in parametric, if you see simple enough equations, you can try to check. Okay, I can make sense of this equation. I can see the roots, right? I can factorize this equation, and okay, this is correct, and you can find the roots here. But anyway, that's the a way to see the parametric equations. Okay. Let me start from here. Another way, I can have like, I will give you these simple equations, okay? If I have this, maybe from 0 to 2 pi. Okay. If you are checking one by one, 0 and then maybe pi over 2 pi, 3 over 2 pi, and 2 pi for each x and y, in which both of them are correlation with the sine and cosine, you will see that it will make a circle, right? It will make a circle. So when the x is 0, y is 1, is 1. Okay. So you will see that this is actually a circle, and distance here, the radius is 1, right? And of course, we can also think like previous examples. We can see this is sine 2t, cos 2t, and we can try to eliminate the t and try to find what is the relation between x and y. Okay? And of course, this is simple enough that you can see if you are squaring the sine, let's say this is the sine. If you are squaring this one, it will be 1, right? So you can see that this x squared plus y squared is equal 1, and that this is our circle right here. Okay. So you can also manipulate the angle, the trigonometric. So any identity that you can find out, you can try to make some relation with them, and then if you want to eliminate the t, you can do that also. Okay. So first is just normal substitutions, eliminations. So that's simple enough, and then the other one is it's related to trigonometry. Okay. The other one is example of the cycloid. Have you heard before? The cycloid, the term cycloid? Yeah, it's related to cycle. Or the best way to illustrate is bicycle, okay? Cycle. So when you ride a bicycle, you can see the movement of the tire, right? So if I draw the circle, maybe here, okay, maybe smaller, and maybe I will draw another one. Maybe another one here. Okay, now imagine you are riding your bike, okay, or your bicycle, and imagine it's circling, right? And it will be moving to the right. Okay. Until this second one. Now, let me draw the, let me make 3 scenario or 3 movement. Okay. So from the position 1, you're moving, at the 2, at the 3, maybe, so you are moving, and let me make this. Okay. So it's ground here, and it's moved to the right side. Okay. Let me check the other color. Let's say green. So if I pinpoint, this is P. Okay. So when it's circling, the P is also circling, and then it's going there, right? So at some point, the P in this position, let's say the number 2, number 3 is random position, randomly, but it will move to the right, and maybe the P here will be, maybe it will be here or here. Yeah, maybe you can check and maybe use some imaginations. Okay, maybe around here. Okay. Okay. Just let's say that way. Okay, let's say that way. So maybe around here. And then the P is circling one more time, and maybe it ends up here, maybe around here. And then what happened is, if I take a curve from this P, connect to this P, connect to this P. Okay. If I take line, okay. So at least the line looks like that. Okay. Now, from here, it's going here, and if you move one more time, going right, then it will make another one. It will make another one. That is cycloid. This curve is called the cycloid. The cycloid. This is cycloid. Okay. Now, because it has a pattern, we can try to find some way to break down what is the component in the cycloid. From just one circle, we can break down to see the relations between the angle, maybe, and maybe the arc, and maybe the radius. Okay. So let me draw one more circle. Maybe here. Wait, wrong. Let's say we have the ground. Move up a little bit. And make it longer. Okay. Yeah, it's different, but yeah. Let's say this is P. The point P is here. Okay. It will be very small to see. Let me draw one more time. Okay. Okay, I think this is better. Too small. Whatever. Let's check this. Let's naming some point. Maybe this O, the center C center, right? D,
maybe Q. Okay. So what I'm going to do is I want to break down this X and Y. Okay. And wait. Uh, Difficult to draw the angle. Okay. This is theta. Okay.
Okay, so there's angle here, theta. So what we are going to do is we want to have, so we want to know the positions of P, okay, in terms of X and Y. So let's say we have some X here and some Y here. And based on our parametric here, the theta and the at least radius, I want to know what's their relations with the X and Y. Okay? So first is, maybe we can start with X. Okay? So X is, if you see from this picture only, oh wait, this Y should be P.
Sorry. The P is on the tire. Okay.
So the X is this line, OT, minus the PQ, right?
Okay. So let me write that. So X is let's say distance OT minus distance PQ. Okay.
Now the interesting part from here, you see OT, okay, it's distance from O to this point, right? And meaning, if you are moving backwards, let's say the circle is starting from here, so it's moving to the right. So at some point from this O, the point O, the circle is moving, right? So which means every arc here from PT, the arc PT, they are stepping OT, right? Okay, that's the logic.
So I can also write the OT is arc of PT. Okay.
But it's stepping the ground, right? Stepping the ground from O to T. Okay. And from the parametric we have, PT, the arc PT, just the radius multiplied by the angle, right?
So I can write this as R multiplied by theta. Or I will carefully
Write the dot and then to sometimes it will confuse you if we are going to factors. Maybe you're thinking, oh, maybe dot product. Oh, no, we are not there yet. Okay. So just R theta.
R theta. We can also write here
The PQ.
maybe I will make it the triangle bigger. So P Q C. So theta there. So if this is radius, then this will be r sine theta, right? Okay. Now I can write x is r theta minus r sine theta. And x is r theta minus sine theta. So that's the first element in cycloid, the x. Okay. Okay. Now the next one is the y. Y is much easier than the x. Okay. Y is CE minus CQ. Okay. Is the radius minus this side. Okay. This side is r cosine. Right? So y is CT or TC is the same minus CQ. It's R minus R cos theta. Now we have two elements in cycloid. So at least in the parametric, okay, you can have parametric in terms of the cycloid. Okay. Or which one is the parameter in cycloid? Which one the parameter? Theta. Theta, right? Theta. The R is fixed. Okay. We don't say the parameter is R and theta. You write a line. You have R is always changing, and you right. Okay. So only parameter here is theta. Okay. Okay. It will be funny if you write okay. The radius is always changing. Okay. Okay. Oh, anyway, is this class better? Better than the previous one, right? Because it's too small. Okay. Now, cycloid. There are several examples, but I think I will go to the directly to 10.2, and we can have another curve example when we are doing the exercise or when you are dealing with your TA maybe. So let me give you the 10.2. It's the calculus with parametric curve. Let me write the general parametric as we previously write. It's x f of t and y is g of t. But dy itself is still f of x. Let me write some definitions. So suppose f and g, let's say just write it's both differentiable. So the key is how to find the tangent line. So let me rewrite all the things that we need to So x is f of t, y is g of t, but y is also a function of x. Okay. Long story short, because we already done in calculus 1, so if you are asking the tangent line, meaning the tangent line is dy over dx. Okay, so let me write this as tangent line, or just this is tangent. Okay. Okay. Now, from the chain rule, we want to find dy dx, and we all have this relation. So we have x with relation with t, y also with t, with y is also with x. So dy dx, if you are to do the chain rule, you can use the dy and relate with dt and dt dx. Okay, right? Okay. Just to refresh the chain rule, and from here we can rearrange, make another formula. Okay. So this is the general formula for derivative, okay, in parametric. Usually it's t, but it depends on what variable you are observing. And the dx over dt, it should not be 0. And maybe you want to simplify and write this as this also okay. Okay, let me give you some really simple example. Okay. Find dy dx at t equal 4. Okay. In this example, because the equation is not too complex or complicated, you can maybe manipulate the form and then erase the t, substitute, or maybe elimination, and you get the relation between x and y. Again, you can find the dy over dx there. Okay. Or you can try the chain rule that you just seen. So you can find dy dx with the help of t. So you can find dx over dt, you can find dy over dt, and use that for finding the dy over dx. Use t equal 4, and you can find the number. Okay. Oh, let me write the. If you want to find the relation between x and y, that's also okay. So you can find y. Eventually, you will get the 2 plus, and you can derive this. Okay. You can derive this, and you can find dy over dx. Or you can find dy over dx is dy over dt over dx of dt. Now, you can right, dy over dt is 1, right? Over 2t minus 2. But we need t equal 4, so we just plug in 4, and it will be 1 over 6, right? Yeah, if you're doing the same thing here, you can also get 1 over 2 x plus 1, but you need to plug in 4 to x. So x is 16 minus 8, which is 8. So this will be 9, 3, and it's still the same, 1 over 6. Okay, so it's the same, so that's correct. Okay. This is just to prove that both way you will have the same answers. Okay. But the parametric one is, it will be useful if you see the equation on t much more complicated. Okay. When you're trying to eliminate t, if you feel difficult, then you can just go here and then get the solutions. Okay. But here's the important part. Okay. That is for dy dx. How about the second derivative? So let me write the x is t squared plus t squared minus 2t, and y is t plus 1. Okay. And let me write dy over dx is 1 over 2t minus 2 from our previous calculations. So what is the second derivative from here? So what is the second derivative? Now, if you are thinking that, okay, we can try to look for the second derivative by taking derivative of 1, it's 0, okay? And taking derivative of 2t is 2. Okay, so it's 0. Is it correct? When you take this as your equations, and you need to derive one more, if you are trying to think like before, you can derive 1 it becomes 0, and derive 2t becomes 2, so 0 over 2, oh, it's 0, right? Right? It seems off, right? Is it correct? Correct or no? Who's agree with this? Anyone agree? Confused? And if it's wrong, what is the wrong? Why it's wrong? And if it's wrong, what is the correct one? What is the correct one? Anyone? Maybe you can think and write some and try some calculation and which one is the correct one. give you a couple of minutes to think and try to see if there's something strange here. There's something strange. I think it's like no, or you don't know. What do you think?
Because it's also details.
DT, the DT.
DT.
Yes. They gave me a DT. Maybe. Okay, good. Okay. Now, the confusion starts because we are treating this as same as when we are dealing with the first derivative. Okay, and what is wrong is we need to break down that the first rule is the y itself is function of x, right? Okay, and you have the x is functions of t, y also functions of t. So when we are using the first definition here, if we are finding the dy over dx, what we are really doing is we are, so imagine this dx is our operations. The derivative of this is the functions, right? So this is the operations and this is the functions. What is really happened in this part is we are derive once more of this. Okay. So if dy dx is equal, that's using the parametric dy over dt, dx over dt, then dy over, let me write here. So this is, let me write one by one so you can clearly see the steps. Make it lower, make it higher. So if we are trying to incorporate the t this will be
Okay? So we need to see that dy over dx in one single equations, because the definition of one equal function of x. Okay? So if we are treating this as just y itself and we just interact by t, we are break down the definition of y is equal function of x. So we need to include that this part is having relations dy over dx. So if you derive maybe three times, maybe or maybe four, the same rules apply. Okay, the same rules apply. So if you try to find the third one, maybe this one becomes the second derivative. Okay. And if you're looking for four, this will be the third derivative. So this will be the rules for the second derivative. So let me make some box here. So second derivative. And let me mark if this one is wrong. Okay, not this way. Now, if we are trying to find the second derivative from our example, then we can write the where is the dy? Okay, so dy over dx is 1 over 2t minus 2. So let me write this. Dx over dt is what? 2t minus 2. So this will be, let me make blue. So minus 2. 2t minus 2 squared. And then 2t minus 2. So it will be minus 2, 2t minus 2. If we are looking for t equal 4 in this second derivative, so second derivative will be 6. 6 is it's 1, right? Oh, wait. Yeah. Okay. Now, let me give you another example that reviewing also your calculus 1. Okay. So you have now knowing the first derivative and second derivative for the parametric. Okay. And remember, the first derivative and second derivative is useful for sketching the curve, right? The first derivative is for gradient. The second derivative is for the concavity. Concavity is when you have a curve, you can have like this one or this one, right? Oh, Okay. Wait. This is 1, right? Right? Correct? Right? Okay. Yeah. I forgot to define. Okay. Now let me give you some example. X is d squared, y is d cubed. So let me write the curve. C is defined by these two equations. Okay. The first question is show that CE has two tangents at 0.30 and their equations. Find the points on C where tangents is horizontal or vertical. And determine where the curve is concave upwards or downwards. And then the last one is sketching the curve. Sketch the curve. So the first one is you have points 3 and 0. So at x equals 3 and y equals 0. You need to show that the curve has two tangents. I need to find the equation. And the second one is find the points on the curve where the tangent is horizontal. Horizontal means the tangent is like this. And vertical, okay. And third one, you need to determine the concavity, okay? When the curve is concave upwards or downwards, okay? And later, because the last one is sketching the curve. Okay? So sketching the curve, the idea is you need to at least get to know about the tangent, the gradient. And the second one is the concavity. Yeah, I think I can give you like maybe around 5 minutes or 10 minutes to check the questions. Yes. The equation only is two. X is t squared and y is t cubed minus 3t.
Okay, let me give you some steps for the first one. The first one is giving the information about the point 3, 0. So x is 3 and y is 0. So from the parametric equation, we have x is equal t squared. So from this one, we can find that t can be plus minus square root of 3, right? So from this t, we can also see that this y is t cubed minus 3t, or we can write this as t squared minus 3. And both of t, the positive and negative square root of 3, when we plug in here, is still the same 0, so it's correct, okay? So this is just a confirmation that this is correct, 0. So we can check the tangent, the dy over dx. So we can use the parametric. So 3t squared minus 3, and x is t squared, so 2t. And we have t is positive square root of 3. Then dy over dx will be plug in square root of 3, it will be square root of 3. And we also need to check the negative one. So dy over dx will be. So this is the two gradients, right? So we have two tangents, and this is the gradient. We have two gradients. Now, on 3, 0, so y is 0, so y minus 0. Let's say this is for t. And the other one will be, so this is the equations. So we have two equations. Okay, now the second one is asking the horizontal and vertical. So horizontal, the tangent should be equal. So this is the gradient like this. So this is what? Yeah, 0, 0. Yeah. And the vertical should be like this one. Okay. You can say infinite or maybe undefined. Undefined may be much better. So we can say it should be undefined. And now, in terms of parametric, the key is to define each y and t and x. So we have dy over dt, and we have also dx over dt. So for the horizontal, this dy over dt should be 0, and dx over dt is not be 0. Let me write one more time, t squared and then y t cubed. And we can look for dy over dt is 3t squared minus 3. It should be 0, so we can find the t. So t will be plus minus 1. So at d positive 1, we can look for the x is 1 and the y is negative 2. And at d equal negative 1, this is the same one, and the y will be positive 2 positions. And dy over dx for undefined one is dy over dt over dx over dt. To be undefined, this should be not 0 and this should be 0. So dx over dt, let me write this, x is t squared. So dx over dt is 2t. Should be 0 and t should be 0, and we get x is 0, 0. So at 0, 0, it will be vertical tangent. And at these 2 points, it's horizontal. Okay, now the next one is the concavity. Or this is the second derivative.
Am I too fast? Or okay? Or need to slow down? Too fast? Am I too fast? Too quick? Or have a confusion? No. Am I too fast at the backside? Too fast or okay? Okay.
Okay, now we deal with the second derivative. So ddt dy over dx and dx over dt. Let me write what is dy over dx. Okay, 3t squared minus 3. For t squared, 60 to t12 t squared. 3t squared. Minus 6, or let me write this, just 2. Hmm, 60 squared plus 6. And we can simplify this, become 40 cubed. Okay.
Okay, now we have the second derivative. But then how do we know what parameter of t that makes the equations going positive or negative? How do we know concave upwards and concave downwards from the second derivative? How do we know? Or let me write concave upwards, concave downwards. Concave upwards if the second derivative is positive, and downwards if it's negative, right? We have these two conditions. But how do we analyze this parametric second derivative? How do we analyze? First, we need to find if this equation equals 0, right? So 0 is the easiest one to analyze. So if we equate this to 0, difficult, right? Difficult, right? But 0 is a good number to approach. Because what? Therefore, t cubed. Can you define for t this way to be 0? But at least we have t should not be 0. So maybe t equals 0 is something. Okay. So let's break that number. Okay. So every time you see any concavity in any calculus, like in calculus 1 and not in calculus 2, and you have this kind of equation in second derivative, what you can do is you need to find some number that when you try to pick that number should not be there. So you can draw the line number. You can draw the line number, and you can write this as 0. So this is t equals 0. Because when t equals 0, it's undefined, right? It's undefined. So it's 0, 3. So 3 divided by 0 is undefined. So keep not crossing this 0, right? Now, we have now special 0 here. So what if t is positive? What will happen? All is positive, right? All is positive. And when t is negative, this will be negative, right? Because of cubes. Because of cubic. The cube make, when you plug in negative, it will be negative. So this will be negative. So t greater than 0 will be concave upwards. And t less 0 is concave downwards. Okay? Got it? Okay. Now I want to this, because this is early calculus 2. And in chapter 10 is actually most of the parts is the same as we did in calculus 1, except all will be in parametric. So I will do some, not really a review, but just a warm up for this calculus 2 to refresh your memory about the calculus 1. Okay? But I will not go in more details. Okay? So this one. And the next one is this the third question? So what's the next one? Is sketching the curve, right? Sketching the curve with what we have. Okay. First, I need to pinpoint any special point that mentioned in the question. So one, maybe one is here.
So maybe 3, and this is 1. Okay. So from what we have done, when it's 1, 2, this is t equal -1, right? And for this 1, -2, this is t equal 1. So at least if you go here, right? And this is the vertical mapping 0, 0. So you will have, or let me maybe look at it. And then at 3, 0, they will have from here and from here. So they will be 2 negative. That's the tangent. This is also the tangent. Yeah, I think that's it. The curve. So you will, if you check some exercise, there will be maybe several curves that have like circling and make some bit like this point. Okay? And the curve maybe not too easy to understand if you see the graphs. Okay? So that's the parametric case. So when you have parametric equations, you can make this kind of loop. And later in the next sections, we will have the polar coordinates. So it's not the x, y, but it's just r and theta. Okay, any questions? If not, I will go a little bit for some parts. So that is this example for the derivative. Okay, the derivative. So this is the integration. Let me write the functions. It's the same with the early functions at the very beginning. I believe this is t squared minus t and y t plus 1. And let's observe t from 1 to 4. So when t is 1, x is -1. When t is 4, x is 8. And let me sketch that functions. So this is -1. Let's say this is 8. And maybe like that.
Yeah, it's the same parabola as the very beginning. Yeah, there's an illustration.
So if you are trying to find the area under the curve, okay, so let's say this is dx and this is y. We know the definitions for the area under the curve, okay? So if you have a to b, this will be y dx, right? If you still remember, from this 2 parametric, we can write down 2 plus square root of x plus 1, right? So we can also check that up. 2 plus 1 dx. Can you integrate this? It's not too easy, right? Okay. We can do some approximations if you want, or maybe using calculator to find some estimations. But
To help or to solve this kind of problem, instead of this way, we can break down the integrations using the parametric equation. So instead using the y dx, we can break down y dx and try to rearrange into dt. Okay?
so let me write the area. Let's say from some t1 until t2. Let me write the formula first. Okay. Or let me write from here, okay, from y dx, okay.
In regard with the chain rule, this y dx, okay, I can, using the dt and dtn, if I relate a y into this t, variables t, I can write down y, the function of t, dx over dt, dt. And this is from t1 until t2.
So, or I can simplify this become
So what you are going to do is you need to plug in y, okay, the y will be a function of t, and then the first derivative of dx of x, okay, so dx over dt, and then multiply by dt. Okay. So you multiply these two and integrate with dt. Okay. So the idea how we can
get this formula. It's actually from here. Okay. From here, this y. Okay. So we can remember the chain rule that dy over dx is dy over dt multiplied by dt over dx. Okay. So we can manipulate or rearrange this y, okay, and putting dt into the equations. Okay. So putting dt into equations. So divide by dt, but multiply by dt. Okay, it's the same thing, right? But then, actually, if we are changing the y into yt, then this formula is makes sense, right? We divide by dt and multiply by dt, okay, from there. So the formula is making sense now. So whenever you find the area under curve, but in parametric, we can relate to this, okay, formula. Now let's check our example. We have this example here. So t is from 1 to 4. Okay. So we can write down integrations from 1 to 4. Yt is t plus 1. And dx over dt, let me write here, is 2t minus 2. So 2t minus 2, and then dt. So we can solve these integrations now. So the area uh, 2t squared, minus 2, right? Okay. And dt, we can solve this to 3. Yeah, you can check the answer. You need some calculations here. $64, 128, 43. It's 120 to the third. Yeah, you can check the answers later. I think I can give you all the basic one, okay? And then maybe after we conclude some chapters for the 10.2 or 10.2, I can give you some exercise if we still have time. Okay, so integrations, this is the formula, okay? And this is the example. Okay. Okay, the next one is the arc length. Let's say the same parabola. From -1 until 8 here. So this is t equal 1. This is t equal 4. So in arc length, you still remember, arc length is the length of this line, right? If we pick some point here, we can have an arc length from
summation of all small lines, right? The small line we call dl. So this is dl. It has two components at least, dy and dx. So arc length, based on what we have done in calculus 1, is integration of dl. Okay. Or let me write the whole formula. dl is with Pythagorean formula. We can derive and we can. I will write the formula. 1 plus dy over dx squared and then dx. Let's say this is x1 and x2. Okay, this is the formula of arc length in general. Okay, in general formula. But what is the arc length formula in parametric? Okay. Arc length in parametric. So dl. Let me break down dl as dy squared plus dx squared. Okay. Instead, directly going into the final formula that we have already know, we can define dy and dx into parametric. Okay. So divide by dt and multiply by dt. So divide by dt and multiply by dt. Okay. And then square. Same way here. Okay. Now we have dt, we can factorize. We can move the dt out. And now we have dy over dt squared and then plus dx over dt squared. Okay. And now we can also move dt outside. So L, or the arc length, will be, let's say, from T1 to T2, square root, big square root. Let me write y prime t plus x prime t squared, and then dt. Okay, and we have now the formula for the parametric. I think it's as long as you know the arc length is, what arc length is. This formula is not too difficult to follow. Okay. Well, you need to do some manipulation for p. Okay. So you define and multiply dt, and that's. I think we can finish up until here. Okay. And some of you still need the code for this course, right? So after this, you can come to me and I will give you the code. Okay. So up until here, the class finished. Okay. Oh, sign.